I see the last group of candidates.
We'll see.
This is why the late rows are
It's consistent.
If they ever put like anything over those windows, I'm not going to know what to do. Cool. All right. Welcome everyone to the Camp Colloquium for March 3rd. Very excited to see you all here. So today we have Giulia and Guidi here from computer science. She's one of our newest faculty members in computer science. Just started off in January. And Giulia's work is really at the sort of intersection of high-performance computing and various scientific applications, specifically ones in computational biology, which is what she's going to be talking predominantly about today, with some work she's done on genome assembly. So with that, and Giulia,
Thank you.
Take it away.
Thank you very much. I'm very happy to be here today. The projector is working. Can you see it right? Okay.
Type something on your screen.
On my screen, okay.
No?
Okay. Okay. Well, great. Every once in a while, we'll need to click. Okay, so today I'm going to talk about parallel algorithms for the novel logarithm genome assembly, and I will introduce the problem a little bit, and I will show how we solve like this problem implementing algorithm using sparse linear algebra. So basically, like a core aspect of my research so far has been like looking at ways of using sparse linear algebra in particular in a non-numerical way. So like in trying to see how we can use this to model problems that are not strictly numerical analysis. And the reason why I'm interested in this is because I believe that like high performance computing today and like recently has been seen like a new dawn. Like historically, like if you think about HPC, high performance computing has been mostly about simulation, so numerical analysis and simulation for like sciences. But today we actually see like many different applications that years ago were not that compute intensive, and so we did not need high performance computing, that today they actually would benefit a lot. And genomics is a prime example of that, because basically until like a few years ago, the physical and chemical process to actually sequence genomes, so starting from a biological sample and getting something that looks like strings of character on your laptop, was very, very expensive. And so you could just generate a very small amount of these strings, and so like your laptop was more than enough, or a small server more than enough to process that kind of data. But we got much, much better at sequencing genome, and now it's very cheap, so people just generate this huge amount of data, but they do not have the expertise or resources to actually like analyze that. And on the other side, we are seeing this increase in heterogeneity, not just in hardware. So instead of just programming CPUs, now it's common to program CPUs and GPUs, for example, in high-performance computing and scientific computing. But it's not just about the hardware itself, it's about the programming models and the languages. And so basically we see this like hourglass where we have a lot of applications, a lot of like hardware and system like knowledge, but the HPC expertise does not scale with the same speed, because it does not scale in terms of like bodies. It's not that like suddenly we have many more people working in HPC, and it doesn't scale with like brain cells, meaning that like every given person, like it's kind of hard. It's like you have to keep learning the many stuff. So it's just not scalable to grow at the same pace. So this is kind of like the high level motivation why I'm interested in looking at ways where we can use things that we know how to do well in high performance computing and scientific computing, like linear algebra, in scenarios that are not historically high performance computing or linear algebra. And this is because if we can map the application, and this is kind of like a 2-point of how I try to address this engine, if you can map this irregular application to computational primitives, then it gets much easier to obtain performance without sacrificing the productivity of the programmer, which is also important. And the other point, which is kind of more at the, like this, you could imagine this first part being more at the interface with the domain scientist, like whoever is actually the domain expert, and this being an interface with like architects and people that work at the lower level. But the idea is like, if we can map this main application on a few primitives, then we need to optimize our programming and our hardware for a few primitives. And so that is going to make it easier to program and easier to get performance. So this is kind of like the two high level, like core things that I will like to do in the next few years. And for today, we focus on the first part, so I'm not going to talk about hardware. And in particular, I will address this problem in computational genomics, which is the Novo genome assembly. Before doing that, I just want to give a little bit more glimpse into the importance of genomics for high-performance computing, or like vice versa, the importance of high-performance computing for genomics. This is how the cost of sequencing the human genome decreased in the past few years, and we saw that it decreased significantly. Now it's fairly cheap. And this generated not only volume of data, which is what we want to deal with in HPC, but also many, many applications, because as we get more data, then people find more creative way of using this data and figure out how they can be useful. So we have many applications, of course, in the human health, but also in biofuel production and agriculture. And it can have a huge impact to being able to sequence things faster, or like to be like more efficient at genomics. Like for example, here, the ability to do this rapid genome sequencing characterization was able to like reduce the cost of hospitalization and, more importantly, the infant morbidity. And there is a more recent work the beginning of last year by Stanford, Santa Cruz, and the Scripps Institute in San Diego that they show how using GPUs they were able to reduce the diagnosis for critically ill patients under 8 hours. And critically ill is kind of the important part there. Like it does make a difference to do it like below a certain amount of time. Okay, so what's this the Novo genome assembly problem that I've been mentioning? So the idea is that when you sequence these genomes with these machines, the machines are not able to just read your whole DNA and output the whole string, which is around 3 gigabytes of characters, like 3 gigabytes of characters. What they do instead is to output the short fragmented sequences. But the idea is that when you do the Novo assembly, it's like building a puzzle, so you have these many small pieces you have to put together, but you don't have the reference. So it's like someone enters in the room right now, drops a huge puzzle with very small pieces on the floor, and then leaves with the box, and we just need to figure out what that puzzle is. It's a cat, it's a dog, it's a landscape, or something else. So this is the first tricky part. And there are, like, if you do have a reference genome, you could possibly use like reference-based, so like mapping to the genome. You could imagine that for the human genome, we do have this, but there has been many studies in the computational bioliterature that shows how a de novo approach is better even when you have the reference. Because when you have the reference, you might basically classify variations, because you might consider something that is actually very important for my genome as an error because that variation does not appear in the reference. Yeah.
So what's the relative size of the pieces to the size of the puzzle?
Yeah, so the genome, for example, for the human genome is 3 giga base pairs, so 3 giga characters. These pieces are no longer than 10,000 characters. And there are two different technologies. The short read technology is like 100 characters for 1 giga. But we are focusing on the long read, which is like up to 10,000.
And are all the pieces from the same box?
Are all the pieces from the same, like in single genome assembly, they are all from the same box. But this process is not perfect. So you do have, like, this is smaller, they have error rates. So like all of these pieces does contain some errors. So when you find a match between two sequences, you might need to figure out whether they actually match or they just look similar because of.
And there are no multiple copies, right? So
there are, and it's redundant, yeah. For account for the errors, we redundantly sample. So basically each, and that's called like the depth of coverage. Sometimes it's just depth or like coverage. And it usually goes between 15 to 60. Of course, it gets more expensive as the depth increases. And what it's telling is that, let's say it is 30, then each location in the genome is sequenced at least 30 times. And there's been like some attempt of making like the assumption that the coverage is uniform, in practice is not really true. So like in most works, people do make that assumption because on average, it is, like you can make it like, you can make some reasonable assumption, but the problem is that you will always have region of the genomes where you have many sequences here, and maybe here you have just a few. So it's not, that assumption is actually not true. And the kind of last piece of complication here comes directly from the biology, meaning that each genome has some amount of repetition. So some part of your genomes will appear multiple times in different locations. And like bacteria tend to have very small repetitions, and plants tend to be all repetition, basically. Yes?
Do we get to design the sampling sequence that we draw these fragments from, or is that determined by like just hardware considerations?
That's the part, that's like all you get is these sequences.
Okay, so we don't know the distribution.
No.
Okay.
What you know is that the depth, the overall depth is like 30 on average, or like 30 or whatever number they will give it to you. So you know that if you do the average of these depths, the average is like some number that they will give you. And I mean, you can work on the length distribution, but you don't have, the error rate is something that you assume from the technology. So it might vary a little bit between like each run.
Okay.
Yeah. So you have very little assumption on the sequences that you are entering.
Okay. Thank you.
And so if you look at this problem, the way it's been like solved for until like recently, this is usually using shared memory software. So shared memory parallelism we didn't know. And this is some like type of runtimes for different species. So bacteria are also usually pretty big to sample, so you might not want to use a supercomputer to sample a bacteria. Human, it starts to get a little bit more tricky, which again, depending on specifically what you're trying to do in terms of the application, 2 days might be a lot or 2 days might be nothing. So that's a little bit dependent. But the thing is like, as we go into plants, these have like huge genomes and huge runtimes. Yes, like onions are bigger than us. Yes, yeah. Like, and this is the biggest genome that we know of so far, which is this Paris japonica plant. Like plants in general like have much bigger genomes, and the idea is that they have a lot of repetitions, and plants have this like added complexity, which we are not going to deal with right now, which is called transpose, which are basically part of the genome that literally moves. And so you have to figure out how to handle that. But the idea here is that in shared memory software, we can still deal with bacteria, human, small plants, but it really does not scale. So the goal is to try to make like parallel computing more accessible to these sizes. And I wanted to mention one thing. Like today in the talk, I will mostly focus on the linear algebra aspect of the computation. There is a bunch of also probability that goes into how you pick certain parameters, which I'm happy to talk about during the question or offline. So basically, the goal here is to be able to find a way to implement parallel algorithms for this problem. Yes.
Just one quick question. You said shared memory twice, and so is it required that you are operating a shared memory setting for the, let's say, the assembly?
No, this is just, I just mentioned it because that's what's popular in terms of state of the art.
Okay.
They're usually like shared memory, but you don't have to. Like shared memories, maybe I should, I meant like shared memory parallelism. So when you use, for example, multi-threading within a single node.
Okay.
That's actually the measure. That's what I meant for shared memory. It's like when you're doing parallel programming, but within a single node. And so the way you do parallel programming within a single node is that you basically assume that different processes can communicate through reads and write in memory. Well, when you go in distributed memory, which is what this work is about, you communicate through messages, explicit messages. So the way you do parallel programming is completely different and arguably much harder in distributed memory. So like everything that we found in the state of the art, which is popular that people use, is currently using shared memory parallelism. Okay, so this is, this is great, but the idea here is that making this, because I remember when I started to work on this, one of the things that people were asking me is well, can you just take one of these shared memory software that are popular in the state of the art and parallelize that and make it distributed memory? But the reality is that distributed memory parallelism programming is not easy, but also these software tend to be very, very messy. These software are usually complex and non-modular. It's very hard or nearly impossible to try to reuse. Let's say that I have this pipeline, which is a true genome assembly pipeline from a group at NIH, which is one of the most popular. And I've been talking to one of the lead developer. This was and I was asking, your software is popular, but it's limited in scalability, so maybe I can work on that. It was you do not want to put your hands on that software. It's years of software engineering to tune stuff, and you really don't want to. And he was, I did try it anyway, but he was right. It was very hard. So, and this is kind of annoying because maybe one software does something particularly well, and you would like to build on that instead of starting from scratch. So this is one of the things that I keep in mind when I build software is how do I make it faster, but also modular, so that if someone likes this part, can just take it and use it for something else.
So did you say that was a TPU or a GPU? This code?
This is software only. CPU only. This one.
And it's still that complicated. Interesting. Oh, nothing. So
Yeah.
it's not an MPI model or something like this.
No, this is just OpenMP. Just a very complex, shared memory. This is just the
so it's still shared memory. Got it. Okay.
Yeah.
Never mind.
This is basically what you see in the state of the art right now. This is the structure. And so for the same reason that it's very hard to reuse stuff, it's also very hard to just go in and modify and parallelize something. Because it's really hard to track whatever effect something that you change here will have somewhere else in the code. And this is, all of this is not just bad for open source community, but it's bad for the software itself, because in the past few years, this genome sequences became cheaper, but also the technology evolved, and we are seeing that very fast. So every year there is some improvement, which might trigger some update in your code to take advantage of that, and so on and so forth. So this is just overall bad for everybody and for a single person that has to deal with it. And so the idea is I think we can solve this problem by using abstraction. And that's not just about performance, but it's also about productivity and modularity. And here are a few primitives and that comes up, computational primitives that comes up pretty often in computational biology. And so the idea is if we can map most of the computation onto a few primitives, then again it becomes easier to optimize for those primitives in terms of performance, easier for the programmer, and better for modularity. And I mostly focused on dense and sparse matrices, and today we'll talk about sparse matrices. So here was kind of the introduction, a little bit long. So here is basically the overall problem. So when we do long read assembly, we start with an input, which are these sequences, which are also called read, biology term. So we have these sequences. The first step is what we call overlap detection, which is basically finding all the pairs of overlapping sequences. So basically, if two sequences have a seed in common, then we will put an edge in the graph. And this overlap layout consensus is the common paradigm for this type of problem. So most of the literature, the software that you find in the literature, in some way implement this paradigm. And
what's the difference between, so each circle is a read, right?
Yeah.
What's the difference between black arrows and red arrows?
So here is, I was marking the transitive edge, because basically when we do transitive reduction, the idea is that we want to remove edges that are redundant, that don't contain extra information. So for example, if we know that 1, 2, and 3 are connected, we don't need the edge from 1 and 2. And this is for this step to simplify. So this is, here, they're within this block, they're exactly the same, red and black. The idea was to mark the transitive edge that we're going to remove for the transitive reduction step. But like in this specific box, there's no difference in meaning in the two. And so once we have this is great, but as you can imagine, because of the errors and the repetition and the amount of data, this is a very messy graph. So finding anything that looks like a genome in that is nearly impossible. So what we do instead, we perform a transit reduction where we remove edges that are redundant. And so what we obtain is a much cleaner graph that then we can work on to generate contigs, which are these like basically longer contiguous region of the genomes. You know, in an ideal world, what we would obtain here is a single string for a bacteria, or like, you know, chromosomes for like other, like for example, for the human. In practice, again, because of the errors and the repetition is a little bit harder. And so what people do after this is a polishing step where you try to understand how to stick these contigs together. And today I will mostly focus about these two steps. And so the way we implemented this is using linear algebra, and the name is called ELBA, the name of the software, which is also an island in Italy, which is very pretty, if you need a vacation spot. But the name actually stands for Extreme Scale Long-Read Berkeley Assembler. And basically the idea here is that we're going to use sparse matrices as the core data structure. Instead of having different like hash tables or like vectors, like move on across the computation, everything will be represented as much as possible as a sparse matrix or a vector when it's needed. And so once we do this, then all the computation can be seen as operation between sparse matrices. And so here we have the camera counting, which is the first step, which I'm not going to go into the details, but the idea of the camera counting is that for each sequence, we are going to extract fixed substrings of length k with a window, basically with a shift of 1. And we're going to count them. So if we have, let's say, A, C, T, G, G, and I want to extract two where, then I will extract AC, CP, DG, and so on and so forth for each sequence. And then we're going to count this. So we will have a hash table that will be the k-mers and the frequency. Then we do some filtering on the frequency based on some probabilistic model that we have created, but I'm going to skip on that. And so the idea of then moving from this hash table representation where we have k-mers to a sparse matrix is that we can obtain greater algorithmic flexibility and modularity, and also better parallelization strategies without a burden on the programmer, because when we have sparse matrix multiplied, like, great, we know how to implement in parallel sparse matrix multiplied. And so here was I was saying about the k-mers. So we obtain these hash tables in the first step where we have the k-mer string that is the key, and the value is the number of times it appears in the dataset and in which read. And so what we do here is that we move from a 1D distributed hash table to a 2D sparse matrix. So right now we have our rows that are the k-mers, and the sequences are the columns, and the non-zero is telling us that that k-mer appears in that sequence. So this is kind of like the overall problem. And now I'm going to go into more details of how we actually do overlay detection with matrices. But if you have any question until now, okay. Just stop any time setting. Yeah.
Sorry, in the graphs that you were showing earlier, so
Yeah.
an edge from one node, so as I understand, the nodes are fragments that you've obtained through the
Yeah.
de novo sampling process,
Yeah.
and an edge from one node to another
Yeah.
means that these two sequences share a substring within them, is that
Yeah.
correct?
Yeah, exactly.
Okay, in that case, could you explain why the graph is directed? Because that seems to be a symmetric relationship between sequences.
The graph is actually we represent it as a bidirected graph.
Okay.
So that was kind of an oversimplification, but it's a bidirected graph. So like it's
Okay.
there are two operations. And
Okay.
when we implemented here like the matrices, we have basically two choices. Either we want to encode the bidirectionality in the edge, or basically make it a directed graph and then have twice as much vertices, where you have like start and end of each read. But like I personally found it easier to think about it as a bidirected graph.
Okay.
But no, but you're right. It's every relationship is symmetric.
Okay, thank you.
Okay. So basically, when we do the overlap detection, we have our matrix A, where we have sequences that are opposed, and the k-mers are the columns. And the non-zero is not just like a Boolean, like true or false, but it's an integer that is telling us where the k-mer appears in the sequence, like which is the starting position of that k-mer. And we know the length of the k-mer because it's fixed, and so we can extract the end position. And this is an information that we need in a basically phase between overlap detection and transfer reduction to filter out some bad candidate. And so what we did is that we have A and then we have its transpose. And what we do is that we multiply the two using like a standard matrix multiplication. And what happens here, and what happens here is that so if you, for example, look at read 2 and read 3, they have two k-mers in common, k-mer 1 and k-mer 2. So what happens if you do a classic matrix multiply? You're going to take the entries, we're going to multiply and add them together, and the output is going to be 537. We can probably stay here a few minutes, hours, weeks, and try to figure out what that means from a biological point of view. And I'm sure it will be fun, but we probably will not come up with anything meaningful. So what we do instead of doing something like the classical matrix multiplication, we use the semi-ring abstraction. So basically, with semi-ring abstraction, we can overload the standard add and multiply operation to do whatever we want, whatever makes sense for our kernel. And so what we do here, instead of our output matrix is going to have a different type. So instead of being another integer, it's going to be an array of pair of int, where we are going to store the positions of the common k-mers and the count, which is going to be how many k-mers I actually have in common. And so basically, the multiply operator becomes an assign. So I take for each k-mer, so in this case, we are looking at k-mer 1. I know that k-mer 1 appears on both read 2 and read 3 in position 15 and 7. And so I'm going to pack them together as a pair and store them in position. And the add become a concatenate. So in this case, there is a second k-mer in common. And so I'm going to also pack its position and ship it back and store it to the position. The idea of the count is that in practice, we only store up to 2 k-mers per pair of sequences. So the count gives us an idea of okay, I have 2 positions, but I actually have 30 k-mers in common. We actually determined empirically that having 30 k-mers didn't actually change the quality of the algorithm. 2 k-mers were enough to determine if the element was true or not. And also, since we're working distributed memory, we want this data structure to be statically allocated and not having, someone that has 3, sometimes it has 5, and so on and so forth. So basically, what we obtain here is a final read-by-read matrix, which is symmetric. So I'm just covering it here to make it a little bit more clear. And what we store is the position of the k-mer and the k-mer count. So here is how many k-mers they have in common, and here is position. So this is the type of information that we're going to use. And here is some results in terms of quality. So the sparse matrix implementation does really not affect this. This is more about how we pick the parameters and everything. But I just wanted to give you a sense that it's doing well in terms of quality and not just performance. So ELBA is this red dot, and for the equalized CCS, which is a technology with very few errors, so below 1% of errors, ELBA is doing pretty well. CLR is a more erroneous old technology with 13% of errors, and we are still doing reasonably well with compared to the state of the art. So we have a recall, a precision of around 77, 78, and precision is basically recall is how many good overlaps we can find, with respect to the whole set of good overlaps between sequences, and the precision how many true ones we found overall. So basically a ratio of good overlaps over good overlaps and bad overlaps that we found. And this is the results, the strong scaling. So here running the code on increasing amount of nodes with the same problem size, and we are comparing ELBA to a 1D, develop 1D, which is basically a distributed hash table implementation of the overlap detection. And what we're seeing is that they're scaling pretty similar. ELBA is about 2 times faster consistently. But I think what's even more interesting that is not shown in the plot is that this is, it took significantly less time to develop ELBA than develop, because develop had to think about, like we had to think about a lot about the fine-grained parallelism in distributed memory with distributed hash table, which was not as nearly as intuitive as sparse matrices. Okay, so so this is basically an actual picture of what an overlap graph looks like for a not even too complicated genome. So basically what we want to do now is to simplify this a little bit with the transfer reduction, because if you look, ideally here you want a single line of nodes. You don't want all this redundancy of like nodes on top of each other. So what we do is that we use the transfer reduction. And so the idea here is that when we get the output matrix, basically after C, we run a pluralized alignment where we filter out stuff that candidate, and we have the result matrix. But this is still like read by read, like sequences by sequences. And so right now it's in a form of overlap graph, and we want to put it in a string graph form, which means that we have no redundant edges and no redundant vertices. So while it's kind of intuitive what's the redundant edges, because you think about like 3 nodes and 1 node can connect to the third, a redundant vertex is a little bit less intuitive in this context. And so the idea here is that a redundant vertex is a sequence which is fully contained into another sequence. Because in this case, R2 is fully contained in R3, so it will not add any information. And so we are going to remove that. That's considered redundant. So we remove those nodes, and already just removing the redundant vertices, it simplifies quite a bit, but there is still, all of these redundancies where you just want linear sequences. And so what we do is that we still use the matrix form. Here we change a little bit what we store in the non-zero. So in this case, what we're going to store is the overhang. So we know that like R1 and R2 overlaps, and at the beginning we were just storing a seed that were in common. Now we're storing this extra length over here, so the suffix of the alignment. And since it's bidirected, in our actual data structure, we will save both of them, and we will deal with it. In practice, I'm going to assume now it's going to be like a directed graph, because it's a little bit simpler to explain. And so basically the idea here is that we want to retain as much useful information, so we're going to define a redundant edge as the edge with the longest suffix. Because if I'm looking, for example, R1, R2, and R3, R1 and R2 have this like big overlap, and the suffix is 30. But if I look at R1 and R3, their overlaps is much smaller, and the suffix is longer of 60. And this is true because we remove contained reads. If we would not remove contained reads, this will not be true. But this holds true since their contained reads are removed. And so basically when we have this 1, 2, 3 type of edge, we want to remove the one with the longest overlap. And the way we do it is again with matrices. So in this case, we're going to, and this is an iterative procedure, so I'm going to go over one iteration, but it's repeated a few times until it reaches convergence. So we have read by read, where we have sequences by sequences, and this is the overhang length. And the first step is to use a summarin that does like mean plus, and the idea is finding the neighbor matrix. The idea is like if I have 2 equivalent paths to go from like A to B, then I want to keep the shortest. And so basically, if I look between going from R1 to R3, I could do R1, R2, and R2, R3, or I could do R1 and R3. And in this case, they are like the same numbers, so I can just store one. But we will store the mean. And like looking at a little bit more how it happens, so here the multiply becomes an addition. So I have R1, like for example, to go from R1 to R4, I have R1, R2, and R2 and R4, and the sum is 100, the sum of the path. But if I do R1, R3 to R3 to R4, it's actually shorter. So I compute the two parallel paths, and then in the add operation, which becomes a mean, I decide to keep the shortest. So that's what I'm going to store in the end matrix. And then after I've done this, I'm basically going to compare element-wise. So in this first operation, we do have communication across nodes. While here it's element-wise, so it's communication-free from a parallelism point of view. And so we're going to look at, we have the original matrix, and then we have this matrix that contains the shortest path. And basically what we're going to see is if something is bigger in the original matrix, bigger or equal than in the neighbor matrix, then it means that that edge is redundant. Because we know that there is an equivalent or smaller, like better path to go from that node to the other node. And so in this case, for example, R1 and R3 and R2, R4 are marked as redundant. And the next operation is basically just multiplying this original matrix element-wise by the negation, the logical negation of I. And so basically you're saying just remove those vertices. And so what we obtain is the string matrix S with our redundant vertices and edges. And again, this is performed a few times because in my head you want to account for like 2, 3, and 4, 5, and like ad hoc neighbors. In practice, it does converge pretty quickly. And so basically we move from this to this, where now we have these strings that are all together. Then the final step that we do here is basically, I'm not going to go into the detail, but just what happens. So now we have these linear chains. We wanted to break them down in order to obtain, here there is like some load balance and communication going on. But basically we want to break them down and then assemble them in longer sequences. And we also do this using sparse matrices. And now we are working on basically improving this phase with a polishing step. And so basically this is what would look like if you would stop at the counting generation. And this is a few more like performance results. So this is for the whole pipeline on Cori and Summit. These are two supercomputers. Cori is like fairly old supercomputer now. Summit is still in the top 10. And again, we're seeing that it's scaling like reasonably well, and then with a little bit like going up toward the end. And these are like C. elegans is a worm, and this is also Tube is a res. And it's also interesting to kind of look at what's taking most of the time in this pipeline. And so this is the same two organism, and we can see that this alignment part, which is a process that is like performed between overlap detection and transduction, is actually taking quite a lot of time. That's a very compute-intensive operation that is very popular in biology. And so I've been working on a GPU implementation of this, and we're planning to publish that like soon. But this is kind of interesting to see how the alignment is taking a lot. But then if you look at the actual matrix operation, even if these matrices are like can be very huge, it's taking very like a relatively little time. So it's a pretty scalable approach. And here is one more result with the H. sapiens. And what's interesting here to say is that, so we saw at the beginning how the runtime varies between like even more than like 2 days sometimes. This is like under like 20 minutes. So we are doing some work to make sure that like we can improve the quality of our output a little bit. But the runtime it's pretty good. So here I conclude kind of the technical part. I just want to summarize a little bit and talk about what I want to do next, and then I'm happy to take any questions. So today we talk about like ELBA, which is this like the Novo genome assembler like software that we designed using sparse matrices, and the results was pretty impressive, like from more than 48 hours to less than 20 minutes. And I would say that like the main takeaway, besides the specific application that I was very excited about, is that if we can do the right mapping, and this is kind of to go back to my initial point, if we can do the right mapping between applications and computational primitives, we can actually significantly improve the scalability without sacrificing the performance of the productivity of the program. You know, it definitely went time into debugging and everything, but like implementing the initial draft of the algorithm using sparse matrices was much simpler than I expected based on my experience with distributed memory parallelism. And And the nice thing about sparse matrices is that they can be very flexible if combined with this with the semi-ring abstraction. And we have been showing that we have not just used sparse matrices for this specific problem, but also for like problem related to like protein similarity search and protein clustering. So and even others, but these are a few of these most successful one that we've been working on. And so it's not just about again, like one specific application and improve the scalability and the programming productivity, but also the fact that this is a very flexible way of implementing algorithm, which was kind of like the point of my dissertation, because I mean, we know that, you know, sparse matrices are graphs and graphs are sparse matrices, and there's been like a lot of effort in mapping specific, you know, individual graph algorithms to linear algebra. But I think that the interesting things here is that like you can actually do that on like end-to-end, like real-world application, not just specific individual standalone algorithms. And kind of like the final point, which goes into more the hardware side, is that once you can map many applications to a single or like a few primitives, then you have a lot of advantages also on the hardware side, because you don't need to like implement in like specific optimization for each possible application or each possible group that works on application. And so basically the whole point is like, if we can do this mapping to computational primitives, it's a scalable approach to kind of widen this hardware graph bottleneck. What is not scalable is to just rely and hope that there will be many, many, many more HPC experts in the future, that like HPC experts can like just hold much more information than they had to. So, you know, which, I mean, I certainly hope that more people will go into HPC and learn about this problem and work on this problem. But I don't think we should rely on that. Like, we should help people getting into this space, lowering the bar of access. So with this, thank you very much, and I'm happy to take any additional questions.
Okay. We definitely have time for questions. Go ahead.
Yes.
Well, I mean, I'm coming from the HPC perspective, so I'm wondering, like, what is the size of the problem you're talking about? Where is the parallelism that you identify here?
Yeah.
And yeah, just a lot of details about how the
Yeah.
things mapped into software and so on.
I just want to get through. Well, I can use this one. Here. Okay, so the size that we're talking about, it varies a lot, like from like species to species. But for example, like for the human genomes, I think we had the number of sequences was in the order of like thousands, like tens of thousands, and then the k-mer space is much, much bigger. So these matrices actually, like when you get to this point, they're big, but they're not like insanely big for like mammalian genomes, and they're also very sparse. But when you do the overlap detection at the beginning, you have a very like short and wide matrix, because the k-mer is much more. So we have like order of millions of k-mers and order of tens of thousands of sequences for the human genomes. As you go with plants, it gets bigger. The second question, the parallelism. Well, here, so all the matrix multiplication or like other operations are done in distributed memory. So this is actually like a distributed sparse matrix multiply. We use the sparse summa algorithm, where basically each processor will have like a 2D chunk of this matrix. And what happens is that, for example, if you are this, like let's imagine like I mentioned before, if you are this matrix and you want to compute this part of the output, what you need to do is just to broadcast your row or your column. Like you don't need like an all-to-all computation. So that's kind of like a very high-level description of the summa. But like the parallelism, it's like everywhere. It's like the abstraction, like in the top, kind of like hide that. But yeah.
In terms of like taking the sparse matrix primitives and kind of plugging them into this genomics problem, you needed to design this custom semi-ring, and how, in order to sort of plug into other problems, like I think you mentioned problems relating to proteins, do you need to design different semi-rings for those, and like how complicated does that design process get?
Yeah, So definitely like the semi-ring can be different for every applications. And it's, I mean, like in my experience, it's not been like terribly hard. It might be one of the hardest parts to think about what exactly, how you translate that. But I think it's usually hard to do it at the beginning. And once you get it, you get it. It's like pointers. Like until if you don't get it, you don't get it. And if you get it, you get it. So
Okay, sure.
it's kind of like I remember when I first started to talk about this with like my advisor like many years ago. It was like, yes, no, we do this and that, and I was like, oh, not following. And then it just like, and now it's like, oh no, everything is sparse metrics, and we can do this and that. So it's definitely like non-trivial at the beginning, but it gets easier as you start to think about the problem as a matrix. Because I think that's the hardest shift. You want to think about like, what does it mean to do a sparse matrix multiply on this graph? So I think it just requires a little bit of like brain training in that. And in terms of flexibility, you can have whatever semi-ring you want. Like for example, like in this specific problem, we didn't even worry about like associativity, like because we found out that it did not impact the quality of the results, and it did not matter for this specific problem. So that was like one less things that we kind of had to worry about, because we can do whatever we want, and we don't need to enforce that limit. But based on your application, you might want to enforce that.
Okay, thank you.
Of course. And basically, like, you can do whatever you want in your semi-ring. The semi-ring is gonna affect, based on which operation you do, is gonna affect your performance. Like, you know, in this case, we were doing very simple operations, and so the impact of the, like, every single operation was not a lot. But of course, if you imagine doing like some big computation within the semi-ring, then it would affect your performance.
Okay.
So now that you have this algorithm set up, when you go to deploy it somewhere, I don't know, like whoever's doing these kinds of computations, what setup do they typically have for computers? Because they're probably not running on supercomputers, right? Like they probably have smaller clusters or something like that. And is biologists doing it, or is it like optical?
So people I've been working with specifically for this problem are from JGI, the Joint Genome Institute at Berkeley, and they do have access to a supercomputer, so they do work on that. But this does not require a supercomputer. Does require like a cluster. I mean, it can also run on a single node if your problem size is small enough that runs on a single node. There's nothing that prevents you from running this software on a single node. I would probably not use this software on a small genomes because of the problem, like at that point, the shared memory software will probably be faster. But definitely this is, you know, it's open source, and there are like a few ways of running. Like if you have access to the supercomputer, we put like, you know, batch job scripts that people can just run, but you can just run it as an MPI job on any cluster. So it's definitely like beneficial if you do have some sort of cluster, and better if you have a good network. So those are definitely like things that are useful if you want to use this.
So it seems like you've gotten a lot of interesting like biological interpretations out of these matrix multiplies on the semi-rings that you designed. Have you seen any uses for like more complicated linear algebra operations, like solves of the matrix or eigenvector solutions?
Well, yeah. So I did have once a conversation with. So I had like the short answer is like no. The longer answer is that like I remember that we were thinking about doing like an equivalent with the semi-ring of Gaussian elimination at some point, which is still on the table. We are just figuring out if it's exactly what we want. So maybe the answer is actually yes, but it's not like out there yet. So we definitely thought about using Gaussian elimination. It did cross our mind at some point to use like eigensolvers, but that really didn't make sense for us since there was no numerical part. So that we didn't really push that idea forward. But I think that possibly you could explore like more like complicated like linear algebra operations.
this is not really matrix multiply in a sense. It's like you don't have the option in the call to the sparse matrix library that says like use the min plus semi-ring instead of, you know, did you have to write the software yourself, I guess, to work on?
So, okay, so like for some of the operation, we use the compblast library, which basically implements sparse summa on sparse matrices. Like during the development, we had to implement some extra parts that were not supported. But that's kind of like another like nice part of this approach is that, you know, like we are not dependent on one implementation. If tomorrow, you know, the greatest, latest, fastest sparse matrix multiply comes out, agreed on, you know, we can map our computation on that. So it's more like, I think like the main like contribution is the conceptual mapping rather than the actual implementation. Like the sparse matrix.
And the modularity is where you.
Yeah. Yeah. The modularity, the fact that is significantly simpler to think about it and to get performance because we, like, the point is like, you know, like, I'm not claiming that I created like a new sparse matrix multiply algorithm, but it's the point like, I know that like, we are good at doing that. How can I use that to solve problems that I'm not numerically now?
Do you see any elements of this problem which could benefit from two-tier approach where you have distributed memory architecture in the top level and then shared memory architecture for some of the subtasks?
Yeah, absolutely. Like this already uses, actually.
Oh, I see.
Yeah. So like this is uses. So like for part of my dissertation, I actually used just MPI, but just because we had a part of the code at the beginning that was not using OpenMP, and so that became the bottleneck. But we then have like I fixed that, so now it runs MPI plus OpenMP, and I'm integrating the GPU support. So
could you give us an example of what you told us? What works better in shared memory?
Well, so like the for example, like in the, so here, basically what's gonna happen is that like about like I mean here is just 2 loops, but like if we divide this in 4, like this is distributed memory because we are limited by the memory, but then all the multiplication happening on a single processor are also parallel in shared memory. So like the parallelism is not just across the 4 blocks, but also within. So like everything is parallel.
The GPU implementation, will that ruin the portability? Because it's so invasive, you have to really...
Yeah, so what, like the GPU, the focus that I have on for the GPU right now is for the alignment, which is not a part that I talked about today, which is between overlap detection and transitive reduction, and that's kind of like dynamic programming. And that will not ruin like anything. Like the code, I already have the code that, you know, like if you want to run on GPU, you will need to compile with CUDA, but then it's like, it's not going to affect how you use matrices. And we have been working with a student like last year, not 2 years ago, and he basically implemented like sparse matrix multiply with semi-ring on GPU. And we have that, but that's still just shared memory. So we can do sparse matrix multiply. Like for example, within this block, we can possibly put this.
I guess I mean like sort of register size decisions, like that's hardware dependent. Won't that kind of ruin a little bit the portability? Like when people are running it on, you know.
Yeah, I mean like that would definitely, like people would definitely need to think about which kind of GPU they might have.
Yeah.
So that's.
It's not like MPI, like GPU.
Yeah, no. Like I mean like. Depending, like, you know, if you have the same type of GPUs, then it's fine.
Sure.
If you don't have, yeah, that would put a little bit of effort on the user to figure that out. But that's very good because that's actually something that I did not think about. So this reminds me that I should make that aware when I release the code. Thank you.
There are no further questions. Let's thank the speaker.
Thank you.